So next speaker is Giacomo Roati from CNR, tunneling transport in strongly interacting atomic Fermi gases.
Hi, good morning or good afternoon, everyone. I hope that you can see the screen and everything is fine.
Yes.
So I would really like to thank the organizer for giving me the possibility to talk here. And unfortunately, of course, I cannot be there, but okay, it's anyway very good to tell you about our experiment about the transport in strongly correlated Fermi gases. So before starting, I really would like to thank all the people that participate to this experimental work, and in particular, Francesco Scazza, Giulia Del Pace, Wujin Kwon, that contribute in the experimental part. And then we had the contribution of Matteo Zaccanti and Willy Zwerger for the theory part of these things that I'm going to discuss. So I don't need to tell you why. I mean, this slide, I mean, is quite obvious for you, but it's just to motivate our work. You know that we can describe any superfluid or superconductor using an order parameter, and the amplitude of this is related to the condensate or the superfluid density, while the phase is in some way related to the superfluid velocity. It's important to say that, of course, order parameter is inside disclose all the microscopic and intimate properties of any state. And in some way, it's shaped by the quantum statistics. And in fact, you can have that inside is contained the excitation spectrum and all the other properties that in some way describe how this system is limited against the dissipation. Well, again, as you know, probably all of you, there are two paradigmatic theories of superfluidity. One is this Bose-Einstein condensate, and the other one is on the other side in the case of Fermi system, is Bardeen-Cooper-Schiffer superfluidity of long-range fermionic pairs. And everything I mean is described in this phase diagram, if you want, in which we have the Fermi temperature, is scaled by the Fermi temperature, and the different regimes are connected and described by a undimensional interaction parameter that is KFA, where KF is the Fermi wave vector and A is this wave scattering length in this case. And so you can have that on this side, below this temperature, critical temperature, you have a condensation of Cooper pairs like, and on the other side, you have the condensation of molecules in case of two-spin component Fermi system. So I will tell you how then in our experiment we use transport measurement to study this transition, and in particular how we could extract important properties of this superfluid state. In general, as you know, transport measurement, and we just listened to one interesting talk about, are important because they are fundamental tools to study intimate properties of the system. So you just want to bring out of the equilibrium the system and you see how it equilibrates in case. And this way we can extract microscopic properties. And these are just three examples that you can find, of course. As you see, I mean, of course, also superconductivity and superfluidity, in fact, were in some way determined by studying transport of current or mass. And now, I mean, again, it is possible to study this kind of phenomenology in many experiments, also with ultra cold atoms that are becoming a quite interesting and powerful, if you want, playground where to investigate transport or quantum transport dynamics. And again, with the ultra cold Fermi system, this became in the last year quite intense subject of study, and there are many experiments, many different realizations. And I have probably forgot some of the results. And again, if you want to have a nice review of this, you want to read this paper by actually one of our organizers of this conference. Well, in our experiment, this is in some ways the only experimental slide about the system itself that we use in Florence. And of course, it is reproduced and used in many other laboratories in the world. We use lithium atoms in two internal states, actually two lowest, that we can in some way identify by spin down and spin up, just to have an idea. And these are, of course, pseudo spin, but these are just named in this way. And then we use flashback resonances that for this state and for this kind of atomic species pretty convenient, that is pretty large and allow us to tune the interaction between spin up and spin down in almost continuous way to access the different regime of superfluidity that I was mentioning at the beginning. So this is a summary. I will tell you how we create a Josephson junction with fermionic superfluids. I will tell about some critical current and condensate fraction and temperature effects measurement. And then in the last probably couple of minutes, if I have time, I will tell you about our recent results on quasi-two-dimensional homogeneous Fermi system. So why Josephson effect? When studying this, I found out that probably the best way to justify this, why it's important to study Josephson effect, is given by Phil Anderson some years ago. And just these 3 lines, in some way, the importance of the Josephson effect is that it provides for the first time an instrument which acts like a clamp for a solid or a coercive field for a ferromagnet. And in particular, the message that I want to deliver you, and I want to also demonstrate by experiment on this system, is that it can pin down the order parameter. Okay, one possible way that I found quite convenient, at least for me, is to sketch in this way. So you have an order parameter, a superfluid or a superconductor or anything that you want, that can be described by an order parameter which has, of course, an amplitude and a phase. Of course, the meaning of absolute phase is absolutely nonsense. So it's very difficult it's impossible to determine the absolute phase of this. But then what can be important, can be done is that you take your system, you split in 2 parts in some way. And then, of course, you will have a left and right order parameter. And if you can, in some way, make the system to interfere, supposing removing, or like it is done in superconductor, to let the system interfere below the barrier. Of course, below the barrier, you will have an interference effect that can be described in general ground using Josephson tunneling energy or coupling energy that is, in fact, proportional to the order parameter of the left and right, modulated by a cosinus that is connected to the relative phase of the left and the right superconductor. So this is absolutely unique quantum phenomenon, and it's considered, this is, I mean, you can read in many papers, like a hallmark of superfluidity and phase coherence. And of course, you can understand, and I will in some way enter in some detail, but from this relation, I don't have, I mean, the other formula here, but this quantity is connected to the critical Josephson energy current, critical Josephson current. That means that measuring a quantity in the lab that is a current, you can access directly to the that is connected to the microscopic essence of any superconductor or any superfluid. So Joseph's effect, I found that is a very powerful tool because connects macroscopic measurable quantity to the microscopic intimate properties of a superconductor or superfluid. And of course, again, you can, and this we have Rosario Fazio with us and is very expert on this. Josephson effect you can consider like then building block to study or to address important phase transition, of course more complicated. For example, superconducting to insulator transition. And the previous speaker was talking about disorder, and of course the disorder Fermi-Hubbard system. Of course, also in the transition from a superfluid to an insulator makes strongly use of the Josephson coupling between different highlands of superconductivity or superfluidity created by the disorder. So that is important, is a very important phenomena, I mean, in quite a different kind of system that you find. So how we talk about the DC Josephson effect, that I probably don't need to tell you what is, but just you consider a superconducting junction, so 2 superconductors separated by a thin insulating barrier. And then you see that inside the Josephson junction, you can have current flowing through without any resistance. Okay, just you don't have any bias potential drop, and that is just the phase difference between the two sides of the superconducting junction that in some way drives and can sustain, if you want, the current. So in some way, the different phase, the quantum phase of the superconductor, in some way is a sort of analog, a quantum voltage analog, I mean, if you want to see in this way. Well, what you can see is that in general, you can have current without resistance that is as a relation of this shape with respect to the relative phase. And you can have that only up to a maximum limit that is the critical Josephson current. And in this plot here, you see a typical measurement that you find in a superconducting junction in which you have the current through the junction versus the voltage. And you see that below critical current, you have current without any voltage drop. And above a critical current value, of course, you start to have the formation of quasi-particle, actually superconductor per-breaking mechanism. And so you have a normal current that follows, of course, the ohmic law. And then, I mean, if I want to write down what is expected to have, considering like the full current in the junction, you will have adjacent terms and then a normal that is related to a conductance or resistance times. Okay, in this case, I just use a difference in chemical potential, but of course, in the case of superconducting junction, you will have something that is proportional to the different voltage. Well, how do we create this? So in my lab in Florence, we have something that now, I mean, many laboratory has, in fact, but is anyway good to have. We have a ultra vacuum chamber in which we create a ultra cold lithium-6 superfluid. And then we can image and we can imprint arbitrary optical potential using digital micromirror devices. Of course, we need to do that with high resolution. And this happens through this microscope objective that is placed close, of course, to the atomic sample. And this is just an example of which kind of potential we can shape. For example, this is the landscape of Florence. And we can do this with quite high resolution. So how do we then produce the Josephson junction? Well, of course, the idea is to shine then a barrier that is very thin, actually few healing lengths, so of the order of 1 micron. And then what we decided to do is, of course, since we cannot inject easily a current, actually it's difficult, we move the barrier. And moving the barrier, this corresponds to a motion, actually a current passing through the barrier. So you see, and this is a movie that you will see on the screen. We move the barrier and you see, I mean, you don't see, but you can in some way see that the density remain almost constant during this motion. So in some way, a critical current that corresponds to a critical velocity of the barrier motion. In some way, the gas flows through the tunneling barrier. And we must do quite slow. And actually, typical velocity are smaller than the speed of sound. Okay, so this is our calculated bus speed of sound. And we move at quite low, much lower velocity, the barrier. If we don't do that, typical, it's just a frozen picture, but you can see that you start to see an accumulation of particles on the reservoir. In some way, the barrier is compressing the atoms in the reservoir on the left. That means that the atoms cannot flow, cannot tunnel coherently from the left to the right. So here I just report the data for a molecular Bose-Einstein condensate. That is one of KF 4.2. I mean, just you can see on the right. So this is the difference in chemical potential between left and right. So in some way is connected to how many atoms are on the left and on the right, versus the velocity of the barrier that I can translate in number of particles or current through the barrier. And you can see that below a critical value, you see that the chemical potential difference is 0. So atoms can flow completely to the barrier. While if I increase the velocity or I increase the current, if you want, I start to see an accumulation, so a difference in chemical potential that grows in the junction. So I will not enter any detail on that, but we can since it's a Josephson junction, we use a typical circuital model that is used in superconducting system. That is the resistively shunted Josephson junction. We have also capacitance here, but anyway, this is pretty the same. There are some equations that we can numerically integrate, and then we can get a fitting function. Actually, we can fit our data. Well, EC is the charging energy is calculated by using the equation of state that is known for this system. And IC and G, so the conductance, are free fitting parameters. So we can extract the properties of the junction using this model. Anyway, just to create the comparison, this is quite strongly reminiscent of what you see in typical superconducting junction, which I was saying before. You have a current without a voltage. Here we have a current without a difference chemical potential. And then, of course, for larger value of current, you start to have a difference in chemical potential and a voltage drop across the junction in a superconducting system. So the other, this is a property, of course, of ultra-cold gases, because typically we forget, but these are gases. And so we can also, in fact, do what I was saying you at the beginning. So I just can remove the barrier and let expand in time-of-flight atoms. And of course, the two reservoirs will interfere. And from the interference, and then I will get an interference pattern. So this is a real matter wave interference pattern, from which I can extract the relative phase dynamics. And then if I do that, I can extract versus, of course, the current or the velocity, that the relation between the relative phase and the current, or the velocity if you want, has a sinusoidal shape. That is, in fact, reminiscent, actually, is what you expect in the case of a Josephson junction or Josephson effect. Another point, okay, this maybe is just a detail, but we can really measure, from this, you can clearly see this. And that means that we observe, we can, in fact, infer that this order parameter has time reversal symmetry. That is what we have, in fact, since our system, our superfluid is an S-wave superfluid. How the exact properties from our measurement? Well, in the case of a BCS system, you know that you can really connect the critical Josephson current with the gap that is proportional then to the condensate fraction by the Ambeckau-Karbalatov relation. Well, what we did, and actually what Matteo Zaccanti and Ilsberger did in this work, they extend this relation to all the BCS crossover. And I will not enter any detail. These are, you can find in this paper, but you can see that you measuring then the critical current, calculating this quantity here, you can extract the condensate fraction. That, by the way, for a unitary system and Fermi superfluid was so far measured by just projecting the unitary superfluid or the unitary condensate or the BCS like condensate on the BC side using a fast ramp in the magnetic field, but was never measured, in fact, in the unitary limit or in the BCS like limit. So, of course, then what we did was to measure, extract from our measurement the critical current for different value of KFA, so different superfluids, from the BC to the BCS. And then we obtain our data set and just have a look to the purple one, I think that you will see like this, that they are corresponding to the higher barrier height with respect to the Fermi energy in this case. And that these lines are the theory from Matteo and from Willi. And you can see that the theory catch quite nicely our data set. And from this, of course, we can invert the relation that was showing you before, and then we can extract, and also in this case, please just have a look to the green diamond, the condensate fraction for different value of interaction, going from the BCS to the BC, and compare with different numerics, okay, that are all explained here. And this is that we finally see that indeed in the unitary system, the condensate fraction is around 50% as expected from theory. So is the strong interaction deplete the condensate that cannot be 100% like in a weakly interacting Bose-Einstein condensate. So as I was showing you at the beginning, so we have this phase diagram, and of course, typically many people, in fact, also including ourselves, work below the critical temperature. And this is what I just presented you. But of course, it is possible also to try to explore what happened around this temperature, around TC, so increasing the temperature of our system. And this was done, and was done in our experiment. We stay at unitarity, so in the stronger correlated regime, so at unitarity. And by using parametric heating, we just heat up the system. In some way, we create a hotter Josephson junction, and we repeated the measurement. So these are the different data sets. So again, just to remind you, this is the difference in chemical potential versus current. And these are the different temperatures from the light blue to the red. We increase the temperature, okay? And you see, okay, the light blue is very close to what I already said to you. So we have a plateau corresponding to the DC Josephson effect. But anyway, the size of this plateau shrink, increasing the temperature, and eventually disappear for sufficiently high temperature, approaching the critical temperature for the condensation. So then, of course, our way to proceed was to plot this maximum critical current that we could see, the maximum current for which we can see a plateau versus temperature. And you see that this decrease and vanish close to the expected critical temperature for trapped superfluid. Of course, in the region, this becomes very complicated. Actually, we have some also some fluctuation, and of course, the critical current is such small that is also not obvious to exactly capture. So this is why we see this. And of course, we have to take into account that the system is not, at least in this experiment, homogeneous, and so this maybe can create some problem or some fluctuation in this point. But anyway, you see a nice drop that probably corresponds to zero, in fact, to the critical temperature to the condensation. And what we did here was to plot this value, the critical temperature versus the interaction. And we nicely see that increase going from the BCS to the BC limit like it is expected. These are the theory line from this work by the group of Stringati in Camerino. Well, again, I want just to give you a comparison, and this is the typical behavior that you see in a generic superconducting Josephson junction. And also here you see a drop of the critical Josephson current moving to the critical temperature. So, I mean, this means that, the systems are quite compatible. Well, so far I just told you about the critical current, okay? So these 2 points, if you want, in this graph. But of course, it is also possible, since we fit our circuit with a circuital model that automatically includes also the normal current, what is the behavior of these normal currents in our system? So this, of course, is due to excitation. And for example, in a superconducting junction, this corresponds to Cooper pair breaking and normal electrons forming. Well, in the case of weakly interacting Bose-Einstein condensate, these currents are dominated typically by phonons. Of course, you don't have any Cooper pair breaking in this system. And this was quite nicely modelized by Meyer and Sverger in this work. And in particular, you have two terms, a term that is the coupling between the condensate atoms and phonons. And then you have you have a contribution that is just due to non-condensed particle, in particular phonons in this case, that is due to phonon tunneling. Again, in superconducting junction, you can recognize the relation that connects the conductance to the gap and to the critical current, and this corresponds to single electrons that are in some way tunneling through the junction. In the case of neutral Fermi superfluid, it was addressed by in this work by one of our organizers, that in particular you can have the contribution of the coupling between the condensate and Bogoliubov-Anderson phonon. And then you would have another term that is just pure to quasi-particle tunnel. Well, our point was what happens in the case of unitary Fermi superfluids. So here I just present you the conductance that we measure, we extract from our data, renormalized by the normal conductance in the sense of a non-interacting Fermi system in our condition. And you see that this conductance, anyway, is always much larger than the one of a non-interacting Fermi gas. It's much, much larger, even above the critical temperature.
Can you soon wrap up?
Finish. So it means that we can have the contribution of bosonic at low temperature. You have that G is much larger than G0, so we expect to have bosonic collective excitation, and G decrease with temperature that is anomalous. And indeed, what we can say, and that is just fast enough, is that even the normal conductance is proportional to the condensate fraction. It's just, you can see from here, well, I just renormalize the maximum critical current with the conductance that is flat and becomes 0 above the critical current, the critical temperature. So if I have just 1 more minute, this is what we are doing now in our lab. So we produce a 2D system, homogeneous, like in other laboratories in the world. We just have work producing in our system, in our homogeneous superfluid, 2 vortex dipole that can collide. And you probably see here. And we call this a quantum vortex collider. We can manipulate nicely the number and the velocity of vortex dipole, and we just studied the collision. And just in the last months, we are working on producing annular superfluid. This is an experimental picture, and we can phase imprint velocity and imprint different circulation or winding number that we can extract then by studying the interference pattern of this rotating superfluid with respect to a non-rotating superfluid. And with this, I want really to thank for the attention.
Thank you very much for the interesting talk. We have time for 1 or maximum 2 questions now. Yeah, Leonie.
Yeah, thank you. It's a beautiful talk. I want to ask maybe not so quick question about the dissipative part of the conductance. When you move a barrier, I appreciate that the superfluid component is just goes through, but there are also you have finite temperature, T is 0.3 TF. So there are also lots of excitations above the condensate, so to speak, right? And those are not going easily through the barrier. So I just wonder, to which extent you see this effect.
Well, okay, maybe I don't know if I need to reshare, but just for the measurement in the first part, we work at 0.08 T over TF. So in some way, we are quite low temperature. I do agree then that when we move to higher temperature, this is in fact is included in our analysis. So we think that by extracting the normal conductance using this circuital model, we can anyway take all the excitation like phenomenological included inside the analysis. But I agree with you that if you want to say, I think that one problem can be the fact that anyway for lower temperature we do not appreciate that the system is not homogeneous. Okay, then of course you will have that the dynamics is more complicated eventually than what we say, because it's not radially is not homogeneous. So longitudinal we can consider like radially, of course, is not, and so we can have some effect on that.
Right. So let me 30 seconds comment. So the question about dissipative conductance at below TC is interesting, and actually you quoted Barnett-Paterna. I mean, it goes back to Josephson. Josephson actually envisioned a dissipative component of Josephson current, which does exist if you bias the junction by chemical potentials rather than phase difference. there are oscillations of the current, but also dissipative component of the current. It does exist. It's very hard to measure in solids. It's probably easier to measure in cold gases. And this is interesting subject for both for experiment and actually for theory.
Yeah, thank you. In fact, I tell you, we want to work that on around the TC, so in the region close to TC, because also maybe some fluctuation are also expected to be due to the fact that we approach, like you say, to the critical temperature. This we want to concentrate on that interval around TC.
Yeah.
Okay, yeah. Thanks.
Can you see some dissipative effects when you are in this? I mean, can you see the heating, some extra excitations in the condensates?
Yeah, so you're right. When you go, did not have time, but of course, when you move higher, when we start with some critical normal current, we also in a previous work we see vortex formation.
Right.
So
okay.
Vortex. The vortex can go out and move inside the bar. And we can nicely see some step, but I did not have time to show.
Okay.
But if you at low temperatures where you have supercurrent and you do this to the barrier, do you see some heating or you
yes,
don't?
exactly.
I never tried. So this is a good point. We could try. I never tried to do.
Yeah. That's interesting.
Okay, thanks.
Okay, thank you. Thank you for interesting discussion. So let's